Hey, welcome back to another episode of Introduction to Computer Networks. This is Holly again, streaming live from NTU. So yeah, good morning, Eneko, Zhuxun, Yanjia, Matthew, Yanjie, and Aslam, and Cassandra, and Junhuan. Yeah, glad that you guys showed up because I accidentally set the starting time to 11:20. Yes, I was looking for ways to change that, but it doesn't appear to be a way to do so. Maybe I can try this. No, there's no way to change the streaming time after I set it. That's very interesting. Yeah, so hey, maybe I can send an email to YouTube and complain about this. Okay, so once I started the session, then I cannot change the starting time. Okay, so hey, welcome Ming Huang, Tasha, Han Zhen, Qingying, Youxuan, and Lucas. Okay, good morning all. So today, there's nothing new except for a very, very gentle heads up. Guys, time is running really fast, in case you haven't noticed. Exam 2 is coming up in about 2 weeks. Okay, so if you click into the Exam 2 channel, you will see that, hey, the exact date and time, the exam scope, and this time I'm a little bit more sure, okay, to which part in the textbook, to which chapter in the textbook we'll cover in the second exam. And the form, regulations, rules will all be the same as exam 1, all right? And you will be joining a Google Meet session, and there's going to be a Google form there where you find the exam questions. All right, good. Now, let's start with the topics today. So again, as we have already started talking yesterday, the reliable data transfer mechanism in TCP, and we'll continue that. So we'll talk about TCP's reliable data transfer mechanism, particularly the sender side, okay, in this set of videos. So the first video is the sender side's finite state machine, all right? And this video is a little bit long, about 7.5 minutes. It's long for a reason because Polly is going to introduce the finite state machine, circles and transitions. And then Polly will describe the finite state machine in a very descriptive way using English. Okay? And then finally, Polly will describe the finite state machine again, but this time transform it into a pseudocode form. It's in a pseudocode such that if you give it to any programmer, they'll be able to program the sender side of TCP. So this is what this video is about. And here, RDT of TCP. These are the characteristics. First of all, it's pipelined. So we send packets back to back in TCP as well. We could have multiple packets in one flight. And the acknowledgement is cumulative, meaning the sequence number in the ACK indicates all the packets below that up to that number are received correctly. And there's only one retransmission timer for the entire flight of packet. And so when that timer times out, then we retransmit the flight of packets. So up to this point, you will probably guess TCP's RDT looks very much like, yep, GBN, the go back in. Now the slight difference is this. In TCP, the RDT adds a little bit something so to speed up the retransmission. And that is a special condition when the sender sees a certain number of duplicate ACKs arriving quickly. Yeah, retransmission timeout, that's not wait for that, that's quickly retransmit. Okay, so this is also called the fast retransmission mechanism. So this is something that's a little bit unlike the standard go back in, but implemented in TCP. Right. Next are the finite state machines of the TCPs. To make it simple, let's ignore the dupe ACK part, okay, the fast transmission part, and let's not talk about the other mechanisms we have not yet discussed that's implemented in TCP. If you are expecting TCP sender looks very much like go back in sender, you're correct. First transition is what? The get call from above transition. Okay, receive data from application. Okay. So in TCP sender, we generate the packet, assign the sequence number to the packet, of course, also calculate the checksum and pass that to the lower layer. So it's essentially the UDT send call. And we check whether the timer has already been started for the flight. If it does, don't do anything. Otherwise, if there's no timer currently running, we're sending a packet, then this must be the send base. Start the timer. And then we increment the next seek num. But in TCP, we are not counting packets, right? If we are counting packets, we add the sequence number by one packet. But here, we are counting the bytes. So we are adding the number of bytes in the data in the packet we're sending out. Now, you see here, I'm trying to be a bit lazy. I did not do the window size check, okay? But in TCP sender, there's also a window size. So there should be an if condition here before creating packet to check whether the next seek num, okay, is still within the window limit, of course. And next, yeah, this is also a familiar transition. This is the transition when the sender receives an ACK. Well, similar to go backend's transition receiving an ACK, that's extract the sequence number from the ACK packet. Now, the action of TCP sender here is different. Only when the sequence number is larger than the send base, meaning this is a new ACK packet. So the sequence number here is something that has not yet been acknowledged. Then we set the send base to the new sequence number because now acknowledgement is received. Sender should say that, slide the send base over. All right. Now, if there are currently not yet ACK packets around, then that's restart timer. So we'll be starting the timer for the new send base. If there are no outstanding packets, so if there are no not yet acknowledged packets around, then let's simply stop the timer. Because this ACK here, acknowledges all the packets that are waiting to be acknowledged. Right? So, hey, looking very simple. That is also saying when y here equals the send base, we do what? Nothing. So if a duplicate ACK is received at the TCP sender, hey, timer does not get restarted, unlike in go backend. Yeah, even though the sequence number is the same, timer gets restarted, refreshed. Okay. And the third transition, again, very typical, this is the timeout transition. So when timer times out, retransmit the entire flight of packet from the send base, and then start timer. This is actually identical to go backend. Yeah, in go backend sender, there's actually one more transition, which is doing what? Checking whether the ACK is corrupted or whether the ACK is a NACK. Okay. In those cases, we do nothing. But you see, yeah, when ACK is received, do these. And when the ACK is new, is doing this. So all these other things do nothing. Is just, saying default actions all ignored. Okay, so from now on, if you don't see any other conditions being listed as a transition here, that means they will be just ignored. Now, this is just another way of writing the finite state machine, but in a pseudocode form. So we switch, different events. There's the data received from above case. There's the timeout case. There's also the receiving of an ACK packet case. So receiving data from ACK, generate packet, set the sequence number in byte count, and start timer if there's not one yet running. Just to make sure that you set the timeout interval to what? The estimated RTT plus 4 times the deviation of RTT. In timeout here, if it is triggered, then retransmit the whole flight of segments and restart timer. Receiving an ACK, extract ACK number. If the ACK number is new, meaning it's acknowledging something that has not yet been acknowledged previously, then update the send base. So we slide the window over. We restart the timer if there are still unacked packets waiting. Otherwise, stop timer. Right? These are the only 3 events. If there are other events occurring not fitting any of these events, ignore. If you're not quite convinced, the previous slide is the pseudocode. This one should convince you. Okay, so what I'm listing here, typing up here, is essentially what the finite state machine is telling. Initialization, and this, it's gonna go forever. It's looping forever, just like every server here, right? Waiting for an event to occur and take the actions correspondingly. It's a switch essentially on the events, and there are 3 different events: getting data from above, timeout, and receiving an ACK. So, from a finite state machine, you can actually convert it to a pseudocode, give this to your programmers, then you get yourself a TCP sender implementation. Right. So
being able to write out from the thinking, from the designing of TCP sender to the finite state machine is essential, because that drawing the finite state machine out of your thinking process is simpler. Okay? Trying to write the pseudocode out of the thinking process, just too challenging. Okay? Once you get the finite state machine, then you can gradually transition that to pseudocode. And there, you are one step closer to getting an implementation of what you were thinking about, what you were designing about.
All right, guys, this is a sudden poll. Okay, do you like the finite state machine way of describing the mechanism better, or the pseudocode way? Okay, Ryan, again, you're on campus, I know, very fast. Okay, guys, tell me, FSM or pseudocode way, which way you like better? So Ryan is saying pseudocode. Yeah, it goes in a time series way, right? Okay. I see some like FSM better, some pseudo. Yeah, and maybe there's a slightly more FSM. I see Aslam explains more that she likes FSM because it kind of tells how the states are related to each other and where the transitions might go. Yeah, pseudo, sure, Heather, we know. Hanjun. Okay, good. Very interesting that you guys prefer one way of describing things versus another. And I'm sure that you all have your own reasons. And some of you might be just based on intuition. Hey, you just, feel like reading a pseudocode. Or maybe you are just more fluent reading pseudocode because you see more mechanisms expressed in pseudocode fashion. But some students might have seen block diagrams very frequently in the earlier life. Therefore, FSM doesn't seem difficult. All right, good. So you see, one mechanism, you can describe it in different ways. Okay, and a lot of times, being an engineer, you also need to know how to communicate to each other. Okay, and if your customer prefers pseudocode, then you present pseudocode. If your customer prefers FSM diagrams, you present SSM. All right, so that's TCP sender side finite state machine, or TCP sender side mechanism. Now that's exercise. Okay, the finite state machine with a couple, to be exact, 3 examples.
As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data sender here. Host B is just sending acknowledgements. Host A here sends one packet starting from sequence number 92. It's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay, so host A here waits until timer fires. And so the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. All right, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So the packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, Okay, we are trying to demonstrate the strengths of using cumulative ACK. That is here. If one of the back-to-back packet that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So to this point here, sender host A here seeing, oh, ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back X, okay, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short, so timeout occurs before X can come back. So first, timer occurred here. Therefore, timeout event in TCP sender's trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Okay. Now, ACK 100, ACK 120 will arrive later. Okay. So when ACK 100 arrive at the sender here, Y equal 100, that is the sequence number in the ACK. The same base at this point is still 92. So Y is greater than same base. Therefore, we change the same base to the new ACK number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, hey, timeout occur, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here, we restart the timer, and this timer is associated with same base 100. When ACK 120 arrive here, oh, okay, we need to change the same base because it was previously 100, and the Y is 120, bigger than 100, so change the same base, slide the window over. Do we stop timer or restart timer? Well, there's no more outstanding packet because there are no more getting called from above. Okay, so, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver, receiver is going to see, oh, data byte up to 99 received. But the thing is, the receiver has already received up to 119. So those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded. And an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when ACK 120 arrives at the sender, well, Y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the 3 transitions, we ignore it. Okay, sender does nothing. The second packet here, with sequence number 100, will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, 100 to 119 bytes have already been passed up to the application layer. So another ACK, 120 is going to be sent back to the sender, and sender is just going to ignore it again.
All right, so that was a couple, 3 examples. Next is actually still RDT's sender. It's some extra, because what we have introduced is a simplified version of RDT. And some of you might be very keen observing that the timeout event, the description is that we start transmitting from the lowest sequence number segment and only that segment. Okay, so third video explains some weird things that we are doing in TCP's RDT. We are not exactly retransmitting the whole flight of packets we've sent before.
And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay? The examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also, okay, explains in example 3. You'll see in the textbook, the authors will describe it this way. When send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back and go back in, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. Okay? The description in the finite state machine says this: retransmit not yet act segment with smaller sequence number. Now we read on the actions being taken carefully. You see, this is not in the plural form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back in. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of condition control. That's defined more precisely what TCP sender does when there is a timeout event. Note that this is no longer the simplified TCP. This one is actually quite realistic considering condition control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting 1 segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way: 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, at the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round-trip time plus 4 times the deviation of the round-trip time. Okay. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh, wow. We were actually quite conservative here already, isn't it? That is what? Covering 99.99 something % of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this: window size dropping all the way to 1 and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more ACKs coming back. That is probably because data cannot go out. But TCP being a pipelined reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of ACKs, or maybe seeing some duplicate ACKs, all ACKs coming back. Not that we get no ACKs at all and then eventually run into timeout. Okay, so timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down. Okay, by reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposing if this is go back in, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus a go back in. So we see similarity being what? Yeah, both of them are pipeline segment, and both use cumulative X, and there's only one retransmission timer, and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. In go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay, so exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously.
All right, so before we talk about congestion control, let's finish delay ACK and fast retransmission. Okay, so next topic is delay ACK. If you noticed, okay, in the previous topic, the mechanism we show is just the sender side. We have not yet shown TCP's receiver side, and TCP's receiver side is very different from go back in because of this delay ACK mechanism. So pay attention to this video, because right after this video, we'll start quiz 24, and the finite state machine of TCP's receiver implementing the delay ACK will be presented as a quiz. All right.
This is the delayed ACK. So this is the mechanism implemented at the TCP's receiver. All right. Now, in order to contrast TCP's receiver to go back end's receiver, let's bring back go back end receiver's finite state machine. And here it is, the go back end's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it out to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go back end does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go back end's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. We're supposed to generate ACK and send the ACK back. But at TCP's receiver, okay, how we send the ACK back depends on the second condition here. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed. Yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. So if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. So let's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, let's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay? The similarity, however, is more the action being taken. Okay? So when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay? Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Okay. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. Okay. The sequence number in the ACK here will be still the latest packet arrived in order. Okay. So this will acknowledge all the packets before that.
All right, so that's delay ACK. Okay, the complication is at sending the positive ACK. Okay, only 2 new data packets, we send 1 ACK. Okay, that is what the delay ACK meant. All right, so there was a question from Lucas asking, the TCP sender so far we've introduced only retransmit when there's a timeout. So Lucas, you're correct. Okay, but there's going to be another topic called fast retransmission. Look at the topic slide here. Number 4, fast retransmit. We will introduce this mechanism, and you will see that TCP retransmits also receiving a certain number of duplicate ACKs. Okay. Now, back to talk about delay ACK. So what I want to say is this. If you recall, in the 3 examples we just walked through before this very last video, there was a scenario where we have ACK loss. So if the ACK loss is happening at the place that there are no subsequent data packet triggering other ACKs, then it's bad. But in the second example, you see that because the ACKs in TCP, just like go backend, is cumulative ACK. So if there are 2 packets sent, the ACK for the first packet is lost, but the ACK for the second packet is fine. Then that first ACK's loss is perfectly fine. It will not influence the operation of the network, operation of TCP. So delay ACK is exactly to exploit that property of go backend, or TCP is a form of go backend. Okay, so sometimes you don't really need to send that many ACKs, okay, back to the sender. And that's why we have this idea, delay ACKing, okay, in TCP. All right, so let's go on to quiz 24. So this is finally to introduce the sender side of TCP. And this, I think, I've been teaching the course for some years, and the students complain there's never a finite state machine for TCP's receiver, not even in the textbook. Okay, so quiz 24 is designed exactly to show you the finite state machine of TCP receiver. So let's try to develop the transitions, okay, and let's start from the 2 transitions that implements the delay ACK. First transition is a fresh data, fresh ACK, where we need to start the timer and set the receiver to the pending state, right? this is therefore, let me make sure. Okay, that's this state. Okay, we are receiving, oopsie. Okay, we are receiving a packet. Okay, this is a receiver receiving a packet from the network. It's not corrupted, and it carries a sequence number that's expected. It's a good packet. Happy. Okay, but okay, you see, it's not filling a gap. That means there's no packet arriving out of order. So this is a perfect transmission so far. Okay, and there's no data packet pending yet. Okay, there's no ACK packet pending to be sent yet. That means this is a fresh ACK we'll be generating. Okay, so let's extract data, pass the data up to the application layer, generate the ACK, that is a new one, carrying the expected sequence number, and then start the timer, right? Increment the expected sequence number and set the pending state to true. Okay, so this is the first ACK. Okay, in case the timer doesn't expire and there's another packet coming in, then we will what? Send an ACK for these two packets. So, and that is done in this second transition. So that's the second event in the delay ACK mechanism. Receiving a packet from network and it's not corrupted. Sequence number is okay, so this is a new packet. It's not filling a gap, but it's a pending state, meaning, hey, there's another packet already starting a timer. Okay, so if this is a pending state, meaning this packet arriving will be generating another ACK, which pairs with the previous one that is pending. Then we generate, of course, the ACK, okay, and send this ACK out instead of sending both ACKs out. But we'll change the pending state back to false and remove the timer. Okay, and other transitions are the same. Okay, as these. Okay, and these are the actions regular go backend receivers would do. All right, so these two transitions explains the two events in the delay ACK mechanism. And then let me introduce this transition. This is the fourth event in the delay ACK mechanism. So if we receive a packet, it's not corrupted, and it's carrying the expected sequence number, but it fills a gap. Okay, the third event is receiving out of order packet creating gap. Okay, the fourth is in case you get a packet that fills a gap. This is what you do. You of course extract the data because this is new data. Okay, you deliver, pass it up to the application layer, and you generate an ACK. But generate to which point? You generate it to the highest sequence number arrived in order. Okay, to the beginning of the next gap. Okay, because there could be multiple gaps, right? You send this ACK, because go backend is cumulative ACK. TCP being go backend runs also cumulative ACK. Okay, so then the expected sequence number next is what? The highest sequence number plus 1. Okay, and of course we change the pending state back to false and remove timer. In case there was a timer set up, a ACK is pending to be delivered. Okay, so this is the fourth event. The third event is covered in this transition, default. If you receive a duplicate, if you receive a out of order packet, what do? You just send duplicate ACK that you have generated before, because out of order you cannot send a new ACK. So if in case there's any timer pending, remove the timer and change the pending state to false. All right, so that was the receiver side of TCP's receiver. Now, Q1 asks, which transition among these four, T1, T2, T3, and T4, so T1 here, T2 here, T3 here, and T4 here, is delaying ACKs, and why? Guys, now you know. It's more important to know why. Okay. Q2. Which transition send duplicate ACKs and why? Which transition sends duplicate ACKs? right. And Q3, which transition sends new egg? So Q2 and Q3, the difference is, it seems that except for this one, right? This one sends an egg. T2 sends an egg. T3 sends an egg. T4 sends also an egg. Okay, so which of these sends duplicate eggs, and which of these sends new eggs? Good. Now, guys, let's go to the discourse space. W9, quiz 24. Okay, we see team 1 already typing things up. Guys, it's okay. Take your time. Okay, we are not looking for fast responders. But in case you are fast, okay, it's okay to type up your solutions. Take your time. You have 5 more minutes to think this through. And for this quiz, I have to say, it's very frequent that people get Q3 wrong. Right? So don't be embarrassed. Don't be embarrassed. As long as you provide a reason, usually people can understand your perspective. And a lot of times it's easy to miss something in your perspective. Okay? So the goal of the quizzes are more for you guys to show your perspectives and observe each other's perspectives so that you can complement each other. All right? So it's okay to edit your solution as long as it's before the due time, Saturday, 6 p.m. Right? 5 minutes in the class. Let's start counting time. Yeah, for this type of quiz, you might want to discuss with your teammates. So, hey, you have multiple people in the team. You can actually collect more perspectives there within the team, isn't it? Okay, guys, a little bit of hint here. Transition T1 definitely generated a new egg, and it sets a timer. and that timer might tick. There might not be another packet here to change the pending state and transmit a cumulative ACK. So in case this timer expires, what's going to happen? Is it going to be handled by T1, T2, or T3? It's not defined, therefore it goes here. So are you sure that this one sent, this ACK packet being sent is always a duplicate ACK? If it's out of order arrival, then it does not fit the condition for T1, T2, T3. So it's definitely this. So in that case, this is a duplicate ACK. But if it's the case of timeout, okay, which is not one of which does not fit the T1, T2, T3 conditions, it will also come here. Okay, so this default transition is special. It handles out of order arrival. It handles also timeout. Okay. So I can see Bo Yao, Team 11, Team 2 are getting it. So obviously Team 11 and Team 2 sees that if this timer times out, because there could be a case that there's a odd number of data packets, right? The last packet would then wait. The last ACK will wait until timer expires and there's a timeout. A new ACK will be sent. It's already generated here. Okay, it's already generated here. Okay, it will be sent. Okay, but it's not T1 there triggering it being sent. It's T4 here triggering being sent. So T4 here generates duplicate ACK, as you guys said for Q2. Yeah, duplicate ACK is generated by T4, but T4 also generates new ACKs. All right? Let's see. Yeah, guys. Yeah, so far we don't have exact the fully correct solutions. Ah, there, Bo Yao. Very good. Guys, Bo Yao's got it right. T4, if the timer started by T1 expires. Okay? Very good. Very good, Team 7. Very good. All right, I think you guys are probably still in the fuzz. Okay, no worries, guys. If you're still wondering why, okay, this is a quiz. It might take you some time. So, my recommendation is to read Team 7 or Team 11's answer, okay, and see if you can discover. Ah, there, Jiaxuan, Team 4 also updated theirs. Okay, good. All right, so for Q3, the correct answer is T2, T3, and T4. And T4 is triggered by the timer started by T1. All right? Yeah, this one is a little bit tricky. But you know what, guys? Introducing the fast retransmission mechanism is going to take some time. So this is already 11:09. Why don't we take a break now? And we'll resume the lecture 11:19, a little bit earlier than usual, and we'll start talking about the last bit of TCP's reliable data transfer, fast retransmit. So this is TCP retransmitting, not just because of a timeout, but also be triggered by receiving duplicate acknowledgements. Okay, good. Let's take a break. let's come back to the lecture. So next is the final piece of TCP. Fast retransmission because of receiving duplicate acts.
Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we were describing, when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice the current value. Okay? Because TCP sender, they're actually considered a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here being a pipeline RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any acts coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. Okay. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out did not hit congestion point? Okay. And we just have a random loss packet in the middle of it. What does the receiver do there? Yeah, it's going to get packet in order, and then a random loss. All the subsequent packet arriving out of order are going to generate duplicate acts coming back to the sender. If you recall TCP sender, when there are duplicate acts, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate acts, and when there is a hidden number of them, then you will probably guess there is a random drop right before the duplicate acts, okay? Or at the first unact segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple acts for the same data, to be more precise, it's triple duplicate acts. Then we resend the unact segment with the smallest sequence number, because this is very likely the lost packet there. Okay. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. Okay. And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate acts coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate acts. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate ACK for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same ACK back to back. So sender here receives the first ACK for 100. And this is the first duplicate ACK, second duplicate ACK, the third duplicate ACK. And this is when we begin retransmitting the first, the smallest sequence number that is unact. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an ACK packet from below. Okay. First of all, we extract the sequence number in the ACK packet. And this is the case when the ACK packet is new. And this is the other case when the ACK packet is not new. So in here you see, we increment the count of duplicate ACKs. Okay. For each duplicate ACK, we increment this by 1. When the count for duplicate ACK is exactly 3, then we resend the segment. So this is fast retransmission of a lost packet. And then of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there's a new ACK. When there's a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see, okay, when there's a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP are these. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout.
All right, so that is the full comparison between TCP and go back in. Okay. Next, two mechanisms to support TCP's reliable data transfer mechanism. First is flow management or flow control. That is to decide the window size at the sender. Okay, and this with this mechanism explains why we need a receive window in TCP packet header. If you recall, there's this receive window field in the packet header, and so pay attention to the video, about 3.5 minutes.
And that takes us to the flow control of TCP. Allow me to explain. Okay, so this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. Okay. If everything is okay, TCP receiver is going to extract data and pass it further up. Okay. What's going on really in the implementation in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Okay. Just like the TCP receiver here is going to push more data into the receiver buffer. Okay. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more, because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So flow control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined, and it's actually the size of the receive buffer space. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher.
All right, so that was flow control. Finally, the connection management. So this is the mechanism to establish a TCP connection. And the second part of the video explains also there's a mechanism to close the TCP connection. And this video is a little bit long because there are two parts. And pay attention because quiz 25 is coming right up.
Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay? At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay? So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, okay, that needs to be initialized. Okay. And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seek num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose an initial sequence number to tell the receiving of the request messages. And it's gonna be sent in a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere. Okay, and that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now, the server will then in the sync received state. So server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. Okay, so sync ACK is such a packet. That is to ACK receiving the sync packet. The server here will be doing yet another thing, choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. Okay. And in sequence number, server tells the client it's going to start from Y. Okay. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is x plus 1. All right, so next seek num is already set to x plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. Okay? And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. So it's just an ACK packet, and the ACK number is y plus 1. Yeah, because this guy here observing the initial sequence number of the server is y, then therefore the next seq num is set to y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close, and ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Okay. Then it's gonna enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Okay. Server here receiving the fin packet sends back an ACK. So ACK bit on, and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Okay, some more ACKs waiting to come back here. Okay, so server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin. It's pretty much done and just waiting for the server to say everything is already sent, so you're okay. So finally, server says done with all the data. Okay, so sending fin. Client here is receiving the fin, sends back the ACK. Okay, saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection?
Alright, so hey, I'll let you ponder why the client needs to stay so long until closing the connection finally. And hey, after following the connection management, connection establishment and connection closing process, now we are ready for quiz 25. You can see that it looks a little bit like quiz 23, isn't it? But this time we'll figure out what is the sequence number for the SYN packet, the SYN ACK packet, and the ACK for the SYN ACK packet, as well as the FIN packet. All right. So here's the problem description. Host A is a client. Let's assume it's a web client, and host B is a web server. So they want to, host C here wants to request something, and host B here will respond with something. So in the request, you see that the request size is 20 bytes. In the response, you can see that the size is 200. But you also see that before they can exchange data, there is a connection establishment process. Okay, and after the exchange is done, right, there's also a connection teardown process. So there's actually more down here. There's a close that needs to be started by the server as well. Okay. So, but I'm asking you only to try to figure out the SYN and the ACK packet sequence number up to this point. Okay. So first is client. The client here sends a SYN packet. So SYN bit is on. And it carries sequence number 29, ACK 42, but it's a SYN packet, so data size 0. It's a control message. There's no data byte. Okay, so host B here needs to acknowledge that SYN. So it's a ACK packet of the SYN, and according to the three-way handshake mechanism, host B here also needs to send a SYN, okay, to inform host A that hey, I'm also willing to start the connection. Okay, so it's not just acknowledging that the SYN is arrived. Okay, It's also to say that, hey, I'm also starting. You need to give me an egg. That's why host A here is sending back an egg as well. Okay, so what is the value of A, B, C, D, E? That is what you need to answer for quiz 25. All right. So let's go to the score space. Okay. Quiz 25, the post is up there. You guys have 4 minutes to think this through and tell me the value of A, B, C, D, E. If you can tell me how you derive it, okay, that will be even better. All right. So let's start counting time. 4 minutes. I think you guys have got it. Yeah, for sing, sing egg, fin, fin egg. These packets don't carry any bytes in the data, but the eggs still need to be incremented by 1. All right, so that is what quiz 25 is about. Good. All right, so let's go on and move on to the next topic. Okay, so you see, chapter 1, there are 2 major problems we spend a lot of time talking about. One is reliable data transfer. We just finished talking about. Next is congestion control. Okay, so in this short video, let me explain what congestion is, why it's such a bad situation, okay, to run into.
Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. Right? So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now when we're talking about network congestion, congestion is occurring here. Routers. And these are the machines that are in the core of the internet. And the resources that we're exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packets waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing.
All right, so that was just to open. Congestion is a bad thing, okay? In the next 3 videos, you will see through 3 scenarios, gradually from unrealistic to realistic, how bad the congestion is. Okay, so let's try to be patient and follow through the 3 videos. So first one is very strong assumption, very unrealistic scenario. Okay.
Scenario 1 is this. Okay, you see here, we have 2 senders, host A and host B, 2 receivers. Okay, so 2 servers receiving requests, I suppose. So 2 senders, 2 receivers. And we do have a link in the middle. The capacity is what? R. And there's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops, because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are 2 flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remained the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Yeah, approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate.
Okay, so you see in such an ideal network where the buffer space is infinite, you might still see long delay and towards infinitively long delay. Now, the second scenario is a little bit more realistic. We now assume buffer size is limited. As a result of that, we will begin to see packet drops. And having packet drops means also that if there's a reliable data transfer mechanism going on there, then retransmission will be necessary. So in the second scenario, you will see congestion might cause the delay to go longer, might cause packet drops, might cause an increased demand of bandwidth.
And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have what? Packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer process is generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in, because it should definitely contain the amount of data we need to send out, and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay, and that goes back and we remove the copy. Right? So this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing, and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the center side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here, because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remain the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into an already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case.
All right. So congestion, not that good, right? So delay and now unnecessary retransmission. Last scenario, you will see something that's even more realistic because on the internet or in a real traffic network, there'll be traffic seemingly irrelevant, but they could be sharing certain links. And as long as you share certain links, you impact each other. Okay, so this is scenario 3.
If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end. Okay, so beyond certain point, the more work you do, you don't get more results. Okay? But here, I'm going to show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. Okay. And each of them is generating a flow traveling multiple hops. So this is one hop, this is the second hop for the red flow. Okay. So multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops, and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Okay. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing and sometimes increasing faster than lambda in. Now what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay? so this is already pretty full when the blue packet just arrived. Okay. And as the lambda increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Yeah, red packet will be dropped, but blue packet what? Will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, yeah, the more output we get. But as it approaches half of R, yeah, we see blue flows, blue packets gets dropped a lot. So originally, not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, okay, than when the lambda in here is small, okay? Really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay, it's all wasted. Okay? The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So, message here, congestion, really, really bad. But what can we do about it?
All right, so it's really bad, isn't it? Right? So if you look at the figure again, lambda input and lambda out. Input means the amount of effort, right? Usually you thought if you work harder and harder, you will get more. But you see, on the internet, in a network, right? If it's, ideal, yes, the more you work, the more output you get, outcome you get. But there's a capacity limit, right? It flattens out. So when there's congestion, okay, when there are packet drops, okay, then it will actually saturate quicker, earlier. In the last scenario you see, because you are all interacting with each other. Okay. So when someone is exaggerated, it would impact you. So whatever you do, being part of a big project will be delayed. So even though you try to work harder, but it will be blocked by other people. So the output can drop like this. Okay, so guys, you see that it's not always, okay, it's not always that you work harder, you get more. So guys, you want to know what your capacity is. That is also saying that at the beginning of the semester, okay, you want to also find a balance in the courses you take, and you want to make sure that you do have the time it needs, okay, to work on the assignments for the course or to prepare for the exams for the courses you take. Okay, otherwise you might run into the saturation case. Okay, even though you try and work very hard, but you get less. Okay. All right, so that takes us to the next quiz. In fact, this quiz is to start, okay, thinking about how we could address the issue, congestion. Okay, so guys, this quiz, Yo Shen, you probably feel, yeah, it's not always that you take more courses, the more you learn. In fact, very often you see that at the end of the semester, it can be frustrating. Okay, but it's okay, Yo Shen, and for the students who suffer from the issue, guys, learn from your experience. At the beginning of the semester, you feel that, oh, these courses are all very interesting. I want to learn, right? That's great. But you want to also stay calm. And you have only this much time. The buffer is limited, guys. Stay calm. think about your capacity. Okay, observe from the past semesters how you handle the course works. Okay, and so you want to be cautious. And a lot of times, taking less safer, and you keep a steady state, and you learn more, and that might make you perform better next semester. In fact, okay, if your intention is to go deeper in a certain subject. Good. So that was a little bit sidetracked, but it's very related to the technical issue we are talking about. But you see, you can relate, right? Let's see how internet address congestion. Then maybe you can address your congestion issue of using your time. Okay, so quiz 26. So this is a question that I try to give you so that you guys brainstorm about how we solve traffic congestion these days. And maybe you get an idea how we can address traffic congestion on the internet, because they are both traffic congestion, right? So you can probably borrow some of the mechanisms we're using already here to that. Okay, you transfer the mechanism from one domain to another domain. Hey guys, we talk about transfer learning, but it's in machine learning AI perspective, but you can always transfer what you've learned from one domain to another domain if you can find the nature of the problem. Okay, so knowing how to abstract a problem, understand the nature of a problem is actually the key towards whether you'll be able to solve a problem independently. All right, so quiz 26. It's about highway traffic. Okay, so I ask you to pretend being a Uber driver, and you are specialized in taking visitors from city center to airport and back. And today, you are on the highway trying to take a customer from city center to the airport, but you discover that it's badly congested. Okay. Now, Q1, I ask, could you name a couple reasons that's causing congestion on highway number 1 where you are stuck? Q2. I mean, it's already congested, right? You can imagine that other Uber drivers or your friends are also Uber drivers would not come taking this route. Okay. Can you inform your fellow drivers so that they can avoid taking this route? Okay, so you are now in the middle of the traffic. Okay, you can imagine packets going through the internet. Okay, the packets or the routers in the middle might have discovered that the delay is growingly longer. Right? How can you tell the sender, hey, slow down or take another route? You see? Association, all right? So if you go to the Discord space, you see that I posted the quiz, and I try to explain. Sometimes we'll have these quizzes seemingly irrelevant to the problems we're talking about. But you know what? They are relevant. Okay? They are relevant in the nature if you abstract the nature of the problem. Okay, so, but it's a take-home quiz because we don't have that much time. Yeah, only 3 minutes remaining. Okay, take your time and solve the problem by Saturday 6 p.m. You can edit your solutions for sure. Okay, the point of the quiz is to allow you guys to brainstorm. Okay, how existing systems address the same problem. Okay, and whether there are lessons you can draw, and borrowing the mechanism into a different domain. And this type of solving a problem, this way of solving a problem is called by association. Okay, human brains are very powerful. You can associate things. All right, great. So I see that if you already start discussing with the classmates, feel free to work on the quiz. Okay, because we have 2 more minutes till the end of the class, but we will not be going over you guys' solutions in this class. Okay, we'll try to go over a few. I'll talk about a few interesting ones beginning next week. With that said, I say goodbye. Okay, bye. Yeah, feel free to type up what you guys have come up with. Okay. Yeah, guys, bye. By the way, you guys might have trouble finding out exactly what your course-taking capacity is. You know what? TCP's condition control has a very special mechanism finding out what is the capacity, okay, to transmit traffic. In fact, one of the quizzes coming up next week is to give you a very interesting game to play to find out what is the right price for a product, a commercial product. And guys, and for that quiz, I'm gonna give you extra points. Okay, those who enter the first phase of the game will win 5 extra points on top of the extra points you are earning already for participation. Those who completed the second phase gets 20 points extra. That means you can probably not participate for 4 more weeks. All right, good. So next week. I think it's the Tuesday lecture. You guys want to come, okay? We'll be playing a game that works in a very similar way how TCP finds the perfect bandwidth, perfect amount of bytes to send in one round. All right, good. Bye. Okay, where's my music? Okay, bye. Yeah, Cassandra, I hope I answered your question, the sing packet and the sing act packets. Okay, if it's still not clear, feel free to ask. Maintenance work, definitely. Accidents with the condition, yeah. And this is the physical limit. Okay, bye, Ali. Oh, great, good to know, Cassandra. I think you're doing better now. Regarding traffic on the chat room, all right. Google Maps. Right. So Google Maps now indicate also the traffic intensity, right, with different colors. Maybe an accident. Yeah, I think Google Map also offers multiple routes, right? Yeah, bye, Cheng'en, bye, Pingxun. Slow vehicles, yeah, so we seem to have more of these slow vehicles somehow. Bye, Homing. Yeah, so maybe there's a line group that all the drivers are on it. Yeah, so you could actually broadcast, okay, don't come up here. It's a huge, gigantic parking lot right now. Okay, I'm gonna stop the stream. See you next week.